Welcome back to the Critical Thinking Tools podcast. This week we're going to be talking about critical thinking in the sciences, distinguishing between the good parts of a scientific discipline and maybe the pseudoscientific parts of the discipline. So we're going to be taking the tools that we learned in previous weeks and applying them to different fields of study and talking about some examples of what could be a real science in that area and what might be a pseudoscience in that area. And also we'll be developing new ideas and new tools as we go along. Part of what we'll be doing today also is commenting on why it's important to address the science that you're studying at the right level of analysis. So for example, you want to address mathematics and physics from a rationalism perspective with some empiricism in there. The more complex a science becomes, let's say biology and psychology, then the gathering of data, massive amounts of data, can be very important in the process of creating a theory out of what you observe. So the level of analysis is very important. You cannot import some of the grand theorizing techniques of physics into psychology, for example, without creating a pseudoscience, or at least risking creating a pseudoscience. We're going to be talking about when rationalism and theorizing is relevant to a science, what level of theory fits with each science. And we're going to be talking about empiricism today too, as a way of dichotomizing these two approaches to science in your mind so that you can think about what's appropriate for which subject. In all sciences, there is a mix of theorizing and empiricism. There's no separating them, but it's still useful to understand that there's a certain way of going about it in each subject that is fruitful, and there's a way of doing it that can be not fruitful or even damaging if it gets applied widely in the population. So we might start talking about the queen of all sciences, which is mathematics, which is not a science itself, but it's a tool of mathematics. And of course, at this level of analysis, rationalism dominates, theorizing, creating axioms, creating proofs out of pure logic is the right level of analysis in mathematics. In an offshoot of mathematics, statistics, you do get into empirical measurement, but as soon as you start to expand mathematics into empirical measurement, you're probably getting into the realm of physics quite quickly. I don't really know of many examples of pseudoscience in mathematics. I think it's difficult to label something in mathematics that, but I do know that some areas of mathematics have become fruitful in the real world, and other areas are so obscure that they haven't translated to practical benefits for society. But nevertheless, even in that very impractical pure math area, I would certainly not call that pseudoscience, as long as it's logically developed. And in the future, there may be some benefit to the purest of abstract math, which is not yet seen to be a benefit to science. So let's move on to the first of the sciences, the most simplest science that deals with the simplest of systems, although it does get very complex, and that is physics. Now, physics has a mix of excellent theories that you would find in physics peer-reviewed articles, some fringe theories that you might find in popular books but not in the peer-reviewed literature, and some pseudosciences. So let's go through some examples of science and pseudosciences in each of these areas. So an example of a pseudoscience in physics might be the flat earth theory that you might come across on some obscure YouTube channel or on social media. And it's a very interesting example of a pseudoscience because it is obviously very testable to measure whether the earth is flat or is round. but it is very much an example of people looking only for confirmation of their hypotheses and rejecting any disconfirming evidence as if it was part of a conspiracy to hide something. So this is how conspiracy theories can harm your critical thinking. You know, if you think that there's a whole group of people working together to suppress the idea that the world is flat, then you can reject any evidence that comes in your way. So it's a sure way to, if you are too suspicious of people's motives, you can come to fall for pseudosciences such as the flat earth pseudoscience. Another tool that we might think of to add to our arsenal here is the idea of parsimony, right? So how parsimonious is it? How simple of an explanation is it? How likely is it? You know, what is the most simplest explanation? That millions of people are conspiring to suppress the information that the world is flat. It's a very unlikely explanation. Or the more parsimonious explanation is that the world is actually spherical and there is no coordination between millions of people to suppress that information, right? So parsimony is an important tool to take forward in distinguishing between what's science and pseudoscience. It's much more likely that the Earth is spherical and that there's a small contingency of people who just enjoy playing with the conspiracy theory that the Earth is flat. I don't know how serious they are about it, but it is a very interesting phenomena of human psychology. An example of a science in physics would be Einstein's theory of relativity, which is very rationally derived from mathematics, and then there's empirical testing later. Then you have quantum theories, also a very successful theory in physics that had a lot of empirical findings that led to the development of a quantum theory hand in hand with mathematical work, whereas Einstein's theory was more mathematics first and then empiricism later. So it can be a mix. Good science can be a mix of empiricism and rationalism at different stages of development. Another area of physics that I would not call a pseudoscience, but it is on the edge of being unfalsifiable, and that is string theory. In an effort to unify the different theories behind the forces in nature, string theory was invented through use of pure mathematics. However, one of the signs of a pseudoscience that might guide you to consider whether this is settled science or not is the fact that it has failed to make specific predictions that are then tested. And one of the constant criticisms of string theory has been that it's not falsifiable yet. It doesn't mean that this area of thought should be eliminated. No, it has too many valid connections to exist in science such that it could possibly be fruitful in the future. But it is lacking one of the elements of a good science, and that's falsifiable, very exact predictions. So at the level of physics and of mathematics, you notice that grand theories such as theory of relativity and quantum theory are very valid and very possible in physics. You find that as you go to more complex sciences, that grand theories become just a little bit more difficult to establish, and maybe it may not be a good idea to try to create grand theories in more empirical sciences like biology and psychology, with perhaps one or two exceptions. Now let's move to chemistry, which is more complex of a science than physics in that you have more interactions between elements and compounds. And let's give an example of a pseudoscience in chemistry to start with. Before chemistry evolved into its current state, people were very motivated to experiment with materials and chemicals to see if they could produce gold out of less valuable materials. And that kind of proto-science or pseudoscience, you might call it, was called alchemy. And through many, many experiments to try and produce things like gold or other precious materials based on very bad theories, nevertheless, all of those hundreds and thousands of mini experiments eventually morphed into modern day chemistry, which became a science when it abandoned some of the ideas from alchemy. It turned out through hundreds and thousands of experiments that you cannot create gold out of anything apart from gold. And that gave people the clue that maybe there's some things that are indivisible and some substances that are elements rather than compounds. And it led to the discovery that some elements like gold are indeed elements and not made up of a few different things. Of course, in contrast, the good theory in chemistry includes quantum theory that also comes from physics. Quantum theory explains how electrons transfer in chemical reactions and so on. It's a beautiful theory that is very exact in. And of course, the grander theory of the whole periodic table is also very reliable and one of the most impressive pieces of science that humans have ever put together. The theory behind the periodic table makes such exact predictions that almost always come to fruition when you put the chemicals together, that it is quite clearly a falsifiable area of science and a very fruitful area of science. These chemical reactions are measurable, the elements are measurable, and the compounds that are created between elements are measurable. So this is good science. Now, if we move on to biology, we might think of some of the good theories in biology that do pass all the signs of being a good science, and then we might look at some examples of a pseudoscience too. So biology is a much more factual science than physics and chemistry in a sense that you have to build up thousands and thousands of facts and observations before you start to get an inkling as to what a grand theory might be. It's not the case in biology that you can create theory from mathematical axioms or philosophical axioms or anything like that. So, for example, when Darwin was developing the theory of evolution, it was a case that he was, first of all, building on the work of earlier biologists who had made thousands and thousands and thousands of observations. They had documented, they had categorized, so he had all of those observations to start to build a theory about how animals may evolve, how we may have originated. But not only that, he then had himself to go out and observe thousands and thousands and thousands of facts and observations through his journey across the earth on the ship the Beagle. Now, it's important that he had some kind of theorizing in his mind as he did so. So it's important that he directed his observations to focusing on why the beaks of birds might vary from one island to another, and tie that to the observations of perhaps how they might have changed over time. So there is some general theorizing that was guiding those observations. That's almost always true in science. But the grand theory of evolution by natural selection and sexual selection could only come as a reliable theory after a lot of gathering of facts and data. And I think this is similar in psychology too. You cannot usually in psychology create a theory from mathematical proof. No, psychology is more like biology, where you have to make a lot of observations that are all guided by a proto-theory. That's actually true. And then you can occasionally come to a new theory in psychology. Now, in contrast to Darwin's quite reliable and quite well-tested theory of evolution, which, by the way, is falsifiable in certain senses, so if you were to find a rabbit skeleton in the deposits of a dinosaur era rock deposit, then you would say, oh, well, I'm going to have to either modify this theory that I have of evolution or abandon it, so also if you found, a layer of alien DNA in early Triassic period, let's say, that showed that alien DNA may have generated life, then you'd have to adapt the theory of evolution. However, so far, the theory of evolution has been tested many times, scrutinized for many decades, and has survived. So it's a good theory at this point. In contrast to this theory of evolution might be a pseudoscientific approach to biology, which might be intelligent design. The idea that because we see such complexity in the creatures of the world and in the mechanisms inside some of those creatures are so complex, only an intelligent designer could have designed that. And this is quite a difficult theory to debunk with some of the tools that we've talked about so far. So we might have to introduce new tools to figure out why is it that intelligent design is not as good as an explanation as Darwin's evolutionary theory. Well, the question becomes philosophical in a sense of if all of what we see in nature, which is quite complex, is created by a designer, then how did that designer originate? Did the designer originate through a natural evolutionary process? In which case, the logic of intelligent design falls down because this very complex being must have evolved. If you think that maybe the intelligent designer was himself designed, then it raises the question of how was the designer of the designer designed, and it becomes an infinite regress. Intelligent design is one of these areas that, of course, is unfalsifiable, does suffer from some of the other signs of a pseudoscience, but you have to think about parsimony, simplicity of explanation, Occam's razor, which is the idea that perhaps the simplest explanation is probably the correct one. You don't want to add unnecessary complexity into an explanation when a simpler explanation will suffice. So in the case of intelligent design, it only adds an extra cog of complexity to the more simpler explanation of evolution from natural selection from Darwin. So as you can see, it can be quite tricky, deciding where to put your beliefs in some of these examples of distinguishing between science and non-science. Now, there may, of course, be some peripheral benefits from believing in intelligent design, some kind of cultural benefit, some kind of happiness that comes from believing in intelligent design. But if you just look at it from a factual perspective, evolution by natural selection is more parsimonious and quite testable too. Now, an offshoot of biology is medicine, and this subcategory of biology is perhaps more complex than some of the simpler systems in biology. So the level of complexity is increasing as we move down the sciences from simple system sciences to complex system sciences. In medicine, you have examples of pseudosciences in alternative medicine. It's usually not in mainstream medicine, although mainstream medicine makes a lot of mistakes over the years too. For example, some drugs turn out to have side effects that people did not know about, and they sometimes find that out 10 years later. So there is, bad science in mainstream medicine from time to time. But an example of a pseudoscience in medicine could be something like homeopathy. So, there's quite a motive to find alternative cures for diseases that come with treatments such as chemotherapy, such as radiation therapy, that are so debilitating that people want to have alternatives. One of those alternatives is homeopathy, which is almost a complete pseudoscience. And it might be interesting to talk about how it is a pseudoscience. So homeopathy is the idea that if you dilute water that has a drop of a substance in it, and if you continue to dilute that substance hundreds of times, then the effect of that minute molecule in the water actually can increase. It doesn't make any sense physically, because when you get to the larger dilutions of these homeopathy cures, you can actually calculate using formula from chemistry that there will be no remaining substance in the water. So it's just pure water at that point, but people still pay money for these vials of homeopathy solutions. So that's an example of a pseudoscience in medicine. It's not really empirical, it's not testable. It is propped up by confirmation bias in those who believe in it, and there's very little attempt in those people who promote homeopathy to put the ideas to an empirical and risky test. On the other hand, there's lots of good science in medicine as well, such as our understanding of diabetes and how that's related to metabolic syndrome, and how that has certain signs in the blood that you can measure with tests to get a quite accurate reading on blood sugar and other chemicals in the blood to diagnose metabolic syndrome or diabetes. And then there is a good understanding of the causes of diabetes too, such as overeating, such as obesity, and other factors too. And you can notice the difference between, let's say, homeopathy and the knowledge that we have about diabetes, in that the molecules in homeopathy are unmeasurable, and the chemicals in the blood in diabetes and metabolic research is measurable with numbers and precise measurements. So that is sometimes a sign of you being in the realm of good science, if you can measure things using numbers and that those measures are quite reliable and valid. And at this level of a science, when you get into medicine, the complexity is so great in the number of possible causes, all interacting in a very complex system, that at this level of analysis, at this level of a science, is vulnerable to pseudosciences, perhaps more so than some of the more basic sciences. When there is uncertainty about multiple causes, you can run into problems of people outside of medicine actually who are not good at critical thinking, coming up with monocausal theories about the cause of certain diseases. You know, some people might come to believe that vitamin C is related to almost all diseases, for example. That's a monocausal idea. And that's similar in psychology too. Psychology, being a very multi-causal science, can be vulnerable to pseudosciences that have monocausal, single cause explanations. And the more vaguer those explanations are, the more that they tend to catch on with the public, the more that they are in the realm of being pseudosciences that are unmeasurable if they do not precisely and clearly set out their theory in terms of measurable constructs, measurable entities. Which brings us to psychology, which is even more complex than biology and medicine, in that the decisions that the mind makes, the processes that go on in the mind, come out of a system of hundreds of billions of neurons that is perhaps the most complex structure in the known universe. Psychology has been vulnerable to pseudosciences in the past, and let's go over one example of them. Let's take Freud's theorizing in psychology. So Freud came up with ideas such as the id and the ego and the superego, and how all of these internal forces in the mind work together to suppress information, to suppress instincts, and so on. And the thing I have to ask you here is, how is Freud measuring the id? How did Freud measure the ego? And how do you measure the superego? If you cannot measure the explanations, the forces, the entities that you are proposing, you may be in the realm of pseudoscience. And Freud also went on to use this vague theorizing to come up with a theory of repressed memories too. The idea that because a lot of us cannot remember very early childhood, Freud assumed that perhaps memories of that time were repressed due to trauma, and maybe this theory explains the whole of human suffering and mental illness in adulthood. And then you have to ask yourself, is Freud talking about measurable entities in the same way that a physicist or a chemist is? And the answer is no. And there is a much better way of doing psychology, and that is to focus on what you can measure. In psychology, like in the theorizing in biology, evidence should dominate the construction of a theory. Of course, you will have a hypothesis on inkling as to what you might be finding, in the same way that Darwin did when he was coming up with the theory of evolution. There's always some proto-theory guiding the collection of data, that's true. But psychology is not like physics. It is not the case that you derive theories from axioms and through pure logic to derive a useful theory in psychology. In fact, it's much more like biology in that you make thousands and thousands of experiments, you make thousands of observations, you measure how this one construct affects another construct through experimentation, and then you slowly form theories that fit within that sub-area of psychology. So an example of a good theory of psychology might be bounded by certain circumstances, and it might be just focused on one aspect of the psychological system rather than being a grand theory of everything. A good example of a good theory of psychology might be the theory of memory consolidation in humans, and also some of the adaptations to that theory through reconsolidation theory. So through observations of people with brain damage, through observations of research in lower mammals, through research of brain scans, through all of these experimental approaches to psychology, including memory research in cognitive psychology, you start to gather information to such a degree that you start to theorize that memory is consolidated through use of the hippocampus for laying down of new autobiographical memories, that it may be permanently stored in the cortex above the hippocampus, not in the hippocampus, and that the amygdala may be an important node that increases the energy involved in laying down that memory. So this is standard consolidation theory that has been adapted by further research in reconsolidation that says that when you retrieve a memory from autobiographical memory, it can be changed slightly when it's reconsolidated into memory. So these are in the realm of being testable theories that are very narrowly focused on one area of psychology, and that is the route to successful theorizing at this level of analysis. Having nice boundaries about the containing the phenomena of interest. It's not a grand theory that explains everything about humans at all times, but it's much more precise, and you can adapt it as you do more and more experiments, and I'm sure it will be adapted in the future too, but it's a good working model as it is. Now contrast that with Freud's very general theory that explains everything about all humans at all times, and you can see the difference. One is a grand theory in psychology that is in the realm of pseudoscience because it's very vague and it has no boundary conditions and it has no conceivable event that could prove it wrong or adapt it in the future. So it remains stagnant as an area of thought, as opposed to consolidation theory that is in the realm of being falsified, and in fact it does get adjusted as we find out more about what areas of the brain are active during the laying down of memories. It's a very difficult problem, but it's open to modification. So that is a real scientific theory in psychology. You notice that these things are measurable, so you can ask participants whether they can remember something. You can scan the brain to see which areas of the brain are active or not active. So it's all in the realm of being measurable entities. It's not easy by any means, but when you put hundreds and hundreds of findings together, you start to develop a theory of consolidation of autobiographical memories. And notice how bound it is in its content. You should not be making grand theories, perhaps with one exception. I think the only exception of what is a successful grand theory in psychology will probably be the theory of the abilities of the mind having evolved from the process of natural selection and sexual selection. So the evolutionary theory is probably the grand theory of all the life sciences, including biology and including parts of psychology too. But other than that, I think the history of psychology is littered with grand theories that went way too far and did quite a lot of damage. So when you had a grand theory from Freud, it tended to do harm when applied in a broad way. Even though behaviorism was a great scientific step forward, the radical behaviorism, which is a grand theory that everything is all about rewards and punishments, that can have practical side effects that are quite negative. And from the development of behavioral psychology into cognitive psychology, there was quite an interesting shift where theories in cognitive psychology tended to be well bounded within a certain area of research, which made them much more testable, much less likely to lead to the kind of cult following that maybe behaviorism generated, or maybe Freudianism generated, or perhaps Carl Jung might be put into the similar category as Freud, in that his theorizing was also, on the grand scheme of things, very much like literature rather than like a science. Now, this is not to say that there's no wisdom in Freud's writing or in Carl Jung's writing or in a modern-day psychologist in Jordan Peterson's continuation of Jung's way of thinking about the world. There may be a lot of wisdom there, but my argument is these are not bound theories that are in the realm of being testable. And finally, there are other social sciences that require critical thinking to pull out the useful, reliable, scientific side of them, and to just have some caution about the grand theories that might come out of these sciences. So, for example, in anthropology, you have very wonderful areas of science, such as measuring the carbon in a substance to determine its age. That's carbon dating. There's DNA analysis that you can do in anthropology, and there's so many wonderful subsciences within anthropology that you can use to build up knowledge that is extraordinarily interesting and in the realm of being modified and testable. But also in social sciences over the last 50 years, you see developments of subdisciplines, such as in anthropology, there's a subdiscipline called critical medical anthropology that is perhaps less of a specific testable theory and more of a grand theory that deals with grand concepts that cannot be measured, right? So, for example, critical medical anthropology starts with the idea that human health is the politically ecological product. So the idea is that human health comes out of a political system that resembles the model that comes from critical theory. And critical theory is a derivative of both Karl Marx's theory of socialism and Sigmund Freud's theory of individual psychology. So as you can see, that's a very grand theory that's dealing with forces that you cannot really measure. The idea of oppression, for example, is not in the realm of science. It's a grand theory. So you might consider that side of anthropology to be in the realm of not science, right? So you might call it a pseudoscience if it claims to be science. You might call it an ideology if it doesn't claim to be science, or you might notice that it has similarities to religion in its moralizing. Similarly, with other social sciences like economics, there is a very interesting, testable side of economics. It's very difficult to test, of course, but there's a very empirical approach to economics, and then there's a very theoretical, grand theory approach to economics that can begin to feel like it is an ideology that is divorced from empiricism. So, for example, in economics, you might consider Marx's theory of money and prices. So Marx's theory of money might focus on how money was invented by the bourgeoisie to be a tool of oppression of the proletariat. So that's one idea. Notice that a lot of these terms are not in the measurable range, are they? They're not really going to be refuted over time. And then Marx's theory of pricing might be that prices are set by the cost of the material and the labor that goes into the material, and that's what determines pricing. And the way that it is written is in a way that is not really open to refutation. It's taken as to be an axiom that is never really refuted in those that believe in it. You know, no matter what happens in society, these beliefs can survive. And when these beliefs lead to bad outcomes, that you can turn that disconfirming evidence on its head and say that, well, it was not done properly in the past. So it can be seen as an unfalsifiable approach to economics. But there are more promising areas of economics that are probably wrong in some way, but at least they're testable and they evolve over time, and they're built on empirical views and combined with better rationalism too. For example, the Austrian School of Economics and the Chicago School of Economics seem to have a more rational explanation of what money is in a way that is more testable and more rational too, right? So their theory of money is that it evolved out of a bartering system, because bartering comes with many different problems. It presents problems because you cannot swap your labor or your skill or your service at just the right time for something that somebody wants to swap with you. It presents a problem. For example, you cannot, as a school teacher, you may need bread when you're not teaching school. So the bartering system naturally creates a need for something to work as a proxy for the value that you give to others. And that proxy should have certain properties, such as it should be portable, it should be divisible, it should be flexible so that it can be changed into different shapes, and it should be weighable perhaps, and it should be fairly rare. If it's too easily available, such as soil or grass, then it would not hold its value, so it needs to hold its value too. And in several different areas of the world, precious metals such as gold and silver emerged as this proxy for value. So that's something that is fairly testable. You can look back at clues from history to see if it has co-evolved. You can look back to track the development of gold as a currency and so on. And you can see that if in other areas of the world it has a similar pattern of using divisible substance that is fairly rare occurred in other cultures too, and then you find that it does. So it's in the realm of modifiable, falsifiable approach to understanding what money is, and it's really lacking in ideology. It's just a descriptive way of explaining how money came to evolve in human societies post-agriculture. And similarly with the Austrian School of Economics and the Chicago Schools of Economics explanation of pricing. So the Austrian school explains that pricing is very subjective. If you choose a product from a supermarket, for example, the first one is probably worth £1 to you. But once you have that product in your basket, then the other products on the shelf are less valuable than that first one because you only need one, for example. So the value to you of the remaining products on the shelf has gone down because it very subjectively changes with circumstances. So that is a quite a testable idea. You can use logic to think it through, and it better explains, really without any ideology involved, that prices are quite subjective to the need of the consumer. So there are, let's say, empirical approaches to economics that, I wouldn't call it science, but I would call it an empirical approach to something that's kind of straddling the humanities and the social sciences. Similarly, in economics, as in psychology, we're dealing with extraordinarily complex systems so that you don't really want to create grand theories. It's not successful, it's not fruitful. And you want to create individual theories that explains parts of economics. So you want a theory that focuses down on predicting inflation, that, like biology, like psychology, takes thousands and thousands of past data points into account to see how inflation might be predicted from government spending, for example, and then you start to form a tentative theory. And I think some areas of economics do take this empirical approach and are quite reliable as a result. I hope you have found this discussion of various sciences and pseudosciences in each of these areas quite interesting. We've introduced new ideas as we've discussed this, such as parsimony, such as the level of analysis that is appropriate for a science. We've talked about the boundaries in theories in the more complex sciences and so on. I hope these tools help you navigate all of these different sciences in such a way that helps you thrive. And thank you for listening.